Hello and welcome to Plan for Success with Automated Test. I am Grant Gothing, Turnkey Systems Manager at Bloomy, and today I'm going to take you through a structured approach that we at Bloomy use for developing automated test equipment. So here's a common situation that we as test engineers often find ourselves in. A customer, colleague, or manager will give us a new product to test, and it seems straightforward until you realize the fine print that's implied. They don't always mention requirements regarding cost, quality, timeline, system performance characteristics, data logging, and deliverables. And if that's not enough, you're often aiming at a moving target due to frequent design changes. So, how do we handle this? Oftentimes, it leads us to jumping straight into developing a solution based on existing components such as an old PXI and manual bench test procedures. The idea here being that the sooner we start implementing, the sooner the project will be done. Unfortunately, that's usually not the case. This approach can lead to miscommunication, scope creep, and budget overage. Instead, let's take a look at a structured approach that we at Bloomy use when developing our ATE. It starts with the initial planning of our requirements and developing of a test procedure. Next, we select our instrumentation, such as PXI or boxed instruments. We then design the interconnects which will route that instrumentation to our unit under test, and we'll go over some best practices for developing our test sequences. Finally, we'll review some guidelines for deploying and documenting our system. Now, before jumping right in, let's take a look at what is meant by functional test, and more specifically, manufacturing functional test. Functional testing verifies that a unit's hardware is operating according to its specifications by implementing a series of test cases which exercise and verify the functionality of each subsystem. What this means is that in a manufacturing setting, we are typically looking for hardware defects which prevent the unit from meeting its specifications. We do this by breaking the unit down into smaller subsystems and testing each of those subsystems individually. Because the focus of the test coverage should be on the manufacturing process, tests which implement design verification or firmware validation should be omitted and left to R&D. Now that we understand what is meant by functional test, let's take a look at the components of an automated test system, which can be broken down into hardware and software. The hardware includes all instrumentation and computing required to test the unit, as well as the cabling and interconnects to route the signals. Low-level drivers are software code modules which are implemented to control each instrument. The test management application then strings together these drivers to create a test sequence unique to each unit under test. Physically, an ATE consists of the unit under test on one end and the instrumentation required to test it on the other. Signals are routed from the instrumentation to the UUT through the cabling, mass interconnect, and oftentimes an ITA or fixture. This grouping is known as the system's interconnects. Typically, the instrumentation, cabling, and mass interconnect will be grouped together into a base system, such as the Bloomy Universal Test System shown on the bottom left. This allows the higher price items to be reused from UUT to UUT by creating interface test adapters that map the mass interconnect signals to the unit under test. Now that we understand the basics of functional test, we will step into phase 1 of the ATE development process, initial planning. The goal here is to define the scope and plan for the project, and we will accomplish this by identifying our requirements and developing a test plan. While it may not be the most exciting part of the project, initial planning is critical to its success. With a solid plan, we can narrow down and define the scope and methodologies of the system, allowing us to reduce development effort and keep a better handle on scope creep. It's very difficult to isolate scope creep in the middle of a project unless the scope is well defined from the start. Including test coverage into our plan will ensure that all functions of the unit under test are covered and that unnecessary tests are not performed. Design and R&D engineers are especially helpful at this stage of the planning process. Planning also helps us to provide realistic cost, schedule, and resourcing estimates to management, customers, manufacturers, and other engineers. Finally, defining our project plan upfront allows us to more easily track our project milestones and deliverables and verify completion. The most logical place to start in our planning process is to define requirements. Requirements tell us exactly what we need to accomplish in order to complete the system. They should be concise, with only one topic per requirement. This allows each requirement to stand alone and be easily understood. Take care to ensure that all requirements are feasible, do not contradict one another, and that each one can be distinctly verified. This will be important during the implementation and validation portions of the project. In general, requirements should define what, not how, and implementation and solution details should be omitted. Requirements should not restrict an engineer by forcing them into a particular solution. When developing a requirement specification, the key is to ensure appropriate coverage. A limited requirement spec may result in a system that meets all requirements but does not function as expected, and an overly constrained system may be more costly or take longer to implement. All project roles such as project manager, engineers, and manufacturing should have input into the requirement specification. Finally, language is important when defining requirements. Shall indicates a critical, contractually binding requirement that cannot be neglected in order for the system to be accepted. Should indicates items which are fairly critical but may be excluded under extenuating circumstances. Finally, requirements that use the may verbiage are nice to haves and can be included if time and budget allow. Also note that should and may can be used to identify suggested implementation details. When defining requirements, there are 4 major categories to include. Project or customer constraints include items regarding objectives, cost, schedule, and deliverables, and typically the project manager will be responsible for these. Operational requirements dictate environmental constraints such as size, weight, and input power, as well as interface constraints such as the HMI and graphic user interface. System requirements pertain to items such as the operating system and programming language, and these requirements are typically specified by the manufacturing or process engineers. The bulk of the requirements will be functional requirements. These define exactly what on the unit will be tested. You should include one requirement for each input, output, or subsystem of the unit, such as power, communications, or analog and digital I/O. There should be at least as many functional requirements as there are subsystems on the unit. Functional requirements are the responsibility of the test and design engineers. Finally, performance requirements dictate the speed, accuracy, and repeatability of the ATE, and may have input from all engineering and management roles. On the left, you can see a requirements template that we have developed at Bloomy to help us keep track of the important information for each type of requirement. From general information about the board to the mechanical and electrical requirements, to operational requirements such as firmware and communications, to the documentation that is available about the board, from existing test requirements and test procedures, to the electrical schematics and cable drawings, to mechanical Gerber files or 3D step files about the board. Finally, there's a section for functional requirements where each subsystem of the unit can be added. Once the requirements are finalized, it's time to develop a test procedure. The test procedure defines how to test each of the functional requirements, what's, that were previously described. While all functional requirements must be addressed, they do not need to be tested in the order laid out by the requirements document. The test procedure will define a logical order and flow for the test that optimizes test coverage and reduces test time. Typically, critical subsystems such as power and communications are tested first. Then subsystems with more likely failures are tested next. In general, the overall test should be separated into subtests, which each test a subsystem of the unit. The goal is to accurately identify failures in the shortest amount of time. The test procedure should include as much detail as available, including communications and signal details, test point names, test limits, and special circuitry. The idea here is to convey all steps required to test the unit as accurately as possible. Test, design, and R&D engineers should all review the test procedure for accuracy and feasibility before any implementation is performed. In addition to defining test details, all reporting details should be specified as early as possible. This includes both the parameters to record as well as the format. Defining the reporting up front helps guide the types of tests that are performed and reduce overall development time. As with the requirements template, Bloomy has developed a test procedure template. Each subtest is broken out with its preconditions and substeps, including command names, requirements, special circuits, and pass-fail criteria. We will now start Phase 2, selecting instrumentation. Here we will choose the instrumentation which best satisfies our requirements for testing the UUT. When defining instrumentation, it is important to know what components and systems are going to be tested and how to test them. In our previous planning, we have already completed this through our requirements document and test procedure. So the next step is to quantify all signal types necessary to test the unit and select the appropriate instrumentation and modules. In general, passive components such as resistors, capacitors, inductors, and even some active components such as diodes may be verified using a digital multimeter. Power inputs to the unit under test can be supplied by either a fixed or programmable power supply. Test unit inputs can be tested using instrumentation outputs and vice versa. For instance, an analog input to the UUT can be verified using a data acquisition card's analog output, and outputs from the unit can be verified using an analog input or a DMM. The same approach can be used with digital I/O. Just make sure to match the voltage levels and output types, such as syncing and sourcing, between your instrumentation and unit under test. Oftentimes, high-speed signals will require more sophisticated instrumentation, such as a scope or function generator. When testing communications, it is important to select an appropriate transceiver. USB adapters and PC cards are available for most communication types, such as serial, Ethernet, CAN, and many other protocols. Finally, if microchips or buses must be tested, JTAG boundary scan may be your best option, though high-speed digital I/O or logic analyzers can also be effective. Once we've identified the types of instrumentation available to us, we must quantify the number of signals necessary to test our unit under test. To do this, we typically use a spreadsheet, where the unit under test's connections are listed down the left side, and the instrument and I/O tapes are labeled along the top. We then assign one or more instruments to each UUT pin. When we are done, we can quantify the required instrumentation. In this example, we connect the UUT's power inputs to fixed 15 and 5 volt power supplies. Signal inputs are connected to analog outputs, and signal outputs are connected to analog inputs. One thing to note is that there are multiple analog inputs available for our instrumentation, which is a multifunction DAC card, but only one analog output. It's fairly common to require more channels than are available on a particular instrument. This especially occurs with DMMs, scopes, function generators, and analog outputs, which typically only have one or two channels. For that reason, we often use switching to extend the channel count of our instrumentation. There are many types of switches. General-purpose relays are probably what we are most familiar with. While these relays work fine for small channel counts, multiplexers and matrices can drastically increase channel count. National Instruments has a great white paper regarding switch topologies, which is referenced on the right sidebar. Here I'll distill down some of this information. Multiplexers, or muxes, are a form of switch which allow us to connect one signal, the common, to many channels. Multiplexers typically come in either a one-wire or two-wire configuration. Think single-pole versus double-pole relays, where in the two-wire configuration, two COM signals get switched to a single channel. This is especially helpful when switching a DMM probe to multiple locations. While only 4 channels are shown here, it's not uncommon to see 32 or 64 channel multiplexers. Multiplexers are among the safest switching option because due to their inherent nature, it is difficult to accidentally short two signals together. However, because of this, they are less flexible than matrices. Matrices are a type of switch that utilize row and columns to connect any one signal to any other, or groups of signals together. Because of this, matrices are much more flexible than multiplexers. For example, let's assume that a DMM is connected across row 0 and row 1. By connecting the appropriate relays, we can measure the voltage from C1 to C3. Now, it would be very easy to measure the voltage from C2 to C3 just by switching different relays. You can see this would allow us to measure many signals against a common ground, which is not necessarily available through a multiplexer. Furthermore, matrices allow us to connect any two columns together. Say our test procedure required a short from column 6 to column 7. This would be very easy to do with a matrix as shown here. However, this flexibility comes with a price, because it's possible to accidentally short two signals together. In our example, what if we forgot to disconnect C2 before measuring C4? You can see that this causes us to accidentally short from C2 to C4, potentially damaging the UUT or test equipment. Therefore, while the matrix is flexible, it requires a higher level of confidence and care than a multiplexer. With all switching modules, there are a few considerations to take into account. Each switch will have different voltage and current limits, so make sure not to exceed these, as doing so may cause the connections to become stuck open or stuck shut. Also, channel count and topology play a big role in selection. As channel count goes up, so does cost. However, with the right topology, you may be able to reduce your switch density. Once we've defined the quantity of signal types we'll need and identified a switch topology that will work for our application, we can select a specific instrumentation modules. NI.com's PXI advisor does a great job of breaking down each type of PXI module and providing specifications to assist you with your selection. If you need more assistance with PXI or need help with boxed or benchtop instruments, local sales reps are a great source of information and can quickly help you identify the right modules for your application. Finally, alliance partners like Bloomy work with this type of instrumentation every day. They have practical experience with a huge range of instruments and can often provide more in-depth assistance than sales reps or online searches. In Phase 3 of our ATE design process, we will define the interconnects that route signals from our instrumentation to our device under test. Signals are typically routed from the instrument through some cabling to a mass interconnect. The mass interconnect provides a generic interface which allows custom interface test adapters, or ITAs, to route the signals to the unit under test. This requires the signal interfaces to be mapped 4 times. First is the instrument pinout, which is typically provided by the manufacturer. Next, the module pinout is where the cabling interfaces with the mass interconnect modules. Third is the mass interconnect receiver map, which identifies all system connections that are available. Finally, the ITA design maps the signals from the generic mass interconnect to the specific unit under test. There are 3 major ways to interface with your instrumentation. A custom interface PCB provides instrument-specific connections that are adapted to a custom connector. The design is highly customized and changes require respinning a PCB. Because of this, there is a large amount of non-recurring engineering, or NRE, required. However, because a PCB is utilized, custom specialized circuitry can be included with minimal extra cost, and the per-system cost after PCB development is relatively low. High-density cables can also be used to interface with instrumentation. This is still a fairly customized design where specific signals from each instrument must be routed to the cable. However, it is more flexible than an interface PCB because the pinout can be easily changed by moving contacts. Because the design is custom, a moderate amount of NRE is still required, and this option has slightly higher per system costs, mainly due to the amount of labor required to create the custom cabling. Finally, the most flexible form of instrument interface is the mass interconnect. This is a modular, plug-and-play receiver where each instrument is connected to a specific module. Off-the-shelf modules are available for a large number of PXI and boxed instruments, greatly reducing NRE. However, while NRE is lower, this solution typically has a higher per-system cost due to the nature of the off-the-shelf components. Even still, the mass interconnect is often the go-to interface for automated test equipment. Here we'll take a look at one example of a mass interconnect receiver, the Virginia Panel G12. This particular mass interconnect provides space for up to 12 modules, laid out in 4 rows and 3 columns. Each module is essentially a mounted connector, and there are many different configurations available, such as high-density 192-pin signal modules, lower-density high-power modules up to 65 amps, and coax and pneumatic modules. In addition, many of these modules have PCB-based interfaces to allow them to easily plug and play with standard cabling to common instrumentation. The first step to documenting the mass interconnect is to lay out the receiver map. This identifies the location of each module. For the G12, columns are labeled with letters and rows are labeled with numbers. In the example here, you can see that we have a matrix in slot A4, communications in slot B1, a miscellaneous block, data acquisition, industrial digital I/O, and power. Unused slots are filled with blanking panels. Because every module corresponds to a particular set of instrumentation, the pinout of each module must be identified. In some cases where an off-the-shelf PCB interface is available, this pinout is fixed based on the instrument and cabling connections. In other cases where the module is more customized, you have a bit more freedom when laying out your pinouts. Let's take a look at one example of a module pinout, the power block. Here we show the system connections for a custom power module. This particular module is a 50-pin micropower with contacts rated to 21 amps. There are 3 rows of contacts laid out as shown here. Each block corresponds to an individual contact of the module, and the information about the connections and signals are provided for each populated contact. It is important to document your module pinouts in an intuitive way, as they will be used often when designing your fixtures and debugging your system. The pinouts of all modules must be defined before continuing on with your design, but when you are finished you will have a detailed map of the entire capabilities of your ATE. This will be used as you transition to the next step, which is designing your ITA, or fixture. Interface test adapters, also known as ITAs or fixtures, are used to route signals from the generic mass interconnect to the specific connections required of each unit under test. Custom circuitry, components, and signal routing can all be accomplished inside of the ITA. There are 2 major methods of connecting to the unit under test: cabling and bed of nails. With a cabled approach, signals are routed to the unit through its external connectors. Internal, non-connectorized signals must be manually probed. A bed of nails fixture, on the other hand, uses spring-loaded pogo pins to contact connectors and internal test points on a printed circuit board. This provides a higher signal coverage than a cabled approach, but costs can be higher due to the custom machining required. In addition, changes to the PCB's layout may require remachining the bed of nails fixture, especially if test point locations change. When choosing your ITA type, you will need to weigh cost, flexibility, and ease of use. Bed of nails is preferred for higher volume manufacturing. However, if the design or PCB layout is likely to change, a cabled approach may be more cost effective. Whichever fixture type you choose, the next step will be to design the physical connections to your unit under test. With a cabled fixture, you'll need to specify the signal details for each pin of the connector on the unit. Next, you must specify the details of the cabling that will connect the unit to the fixture, using either a wire run list or schematic. For a bed of nails fixture, you must specify the probe layout. This drawing provides the location and signal names of all test points and connectors necessary for testing. The probe layout is best represented using signal callouts overlaid onto the PCB's Gerber or DXF drawings. While it's often not necessary to contact every test point, the bed of nails fixture should be drilled for all points to account for expansion or changes in the future. Once the physical connections are defined, you can fill in the details of the signal routing and circuitry inside the fixture. When designing the fixture circuitry, there are several personnel roles to take into account: the design engineers who developed the device, software and test engineers developing the ATE, as well as the manufacturing technicians who will be assembling the fixture. Each role will require different information, and it is important to satisfy their requirements. While there is no one way to design the fixture circuitry, there are a few guidelines to follow. Schematics are the preferred design approach because they provide a visual representation of the connections. This is most helpful when conveying your design to fellow engineers or management. Because the major purpose of the fixture is to test the UUT, schematics should be designed from the UUT's point of view. Sheet organization is especially important on larger fixture schematics. Organizing pages by functionality can greatly improve readability. Assembly technicians may prefer to wire the fixture using wire run lists rather than schematics. Wire run lists make it easier to keep track of each connection and provide a means of rigging out the fixture. Using a tool that maintains net or signal names, such as PCB design applications, often allow the signals to be exported into net lists or wire lists. Furthermore, these tools will often keep track of all components, helping you maintain an accurate bill of materials. Finally, you should comment your schematics just as you would comment software. Circuit designs are not always intuitive, and the goal of your schematics is to explain how you will be using the instrumentation to test your device. These comments will be especially helpful as you start to develop your test code. Which leads us into Phase 4, Code Development. Here we will go over best practices for implementing an automated test procedure. To start, let's take a look at the major software components of an ATE. At the lowest level, you have driver software, which interacts with your hardware. Independent drivers should be developed for each instrument, and drivers should not know about one another or about the overall system. Instead, they should only implement the basic functionality for their particular piece of hardware. Device interactions should be implemented as part of a hardware abstraction layer. Here, individual driver functionalities can be combined to create more complex capabilities. It is a good idea to abstract the channel and instrument signal names out into human-readable aliases. These aliases should be test-specific, allowing the developer to understand the signals from the unit under test's point of view, rather than the instrument's point of view. For example, instead of referencing analog input 27 on your data acquisition module, the hardware abstraction layer can allow a developer to reference a human-readable representation of AI27, such as downstream pressure transducer. Therefore, when developing a test sequence, it is easier to understand what is happening from a real-world perspective. Furthermore, by abstracting the hardware channels using aliases, physical changes to instrumentation have less of an impact on software, as only the alias map will need to change. On top of the hardware abstraction layer is the test sequencing framework. Here is where code modules are strung together to create a complex test sequence. Typically, the test sequencing framework will have two modes of operation: test development and test execution, or runtime interface. National Instruments Test Stand accomplishes both roles and provides all necessary capabilities for developing and executing test sequences. Not only does NI Test Stand allow the development and execution of test sequences, but it provides a wealth of other features beneficial to automated test design. Features such as report generation, including database connectivity, property and limit file management, and user control. The development interface allows easy drag and drop editing of sequences, and the built-in templates and examples help speed development time and assist in developing complex applications. The purpose of your test code is to utilize your instrumentation to verify the functionality of your unit under test. This is accomplished by implementing your predefined test procedure using the hardware drivers and test sequencer available to you. By following a few guidelines, your code will not only be functional, but it will be easily readable and intuitive to maintain and operate. Tests should be implemented as subsequences laid out by your test procedure, paying close attention to test flow, limits, and data logging or reporting requirements. Steps should be given short but informative names, allowing operators to quickly identify unit failures when they occur. Step names should reference the components or subsystems that they are testing. And because products and tests are constantly evolving, care should be taken to allow the code to quickly adapt to changes and scale up or down in the future. Now that we've finished discussing the design and implementation of your ATE, it's time to review the final phase, deployment. System deployment is often left to the end of the project where budgeted time is low and the deadline is getting tight. However, deployment always seems to take longer than you'd think. Executable and installer build scripts can take several days to perfect, and finalizing your documentation isn't always trivial. By planning for deployment from the start and even including it into the project budget, you can avoid some of this last-minute stress. Keeping your system organized and performing incremental builds and deployments along the way will help make the process more familiar to you. Finally, each customer, department, or end user is different. Acceptance testing and validation are critical to getting sign-off. Define these procedures early so that you can see what you're aiming for and there are no surprises at the end. The idea is to have a smooth transition from engineering to manufacturing. So, by taking a structured approach to ATE development, from requirements gathering through system deployment, you can reduce risk and scope creep, improve project performance, and create a robust, maintainable test system. There are many resources available to help you along your way, from instrument vendors and online white papers to user groups and alliance partners. Whether you do it yourself or enlist some support, be sure to keep your approach structured. And remember, if you don't have time to do it right, when will you have time to do it over? Thanks for watching Plan for Success with Automated Test. I'm Grant Gothing, Turnkey Systems Manager at Bloomy, a National Instruments Platinum Alliance partner.